Back into the man I things that I said I wouldn't do, I did them. Secrets below the surface, the truth I hid them. As mankind has passed, the can erase the tears of a million years. This human race of animals that talk and walk upright, the slave or date and fall in the trap.
Hello and welcome to the practice problems video on Stokes' theorem, or Stokes' theorem. So in this video, I actually only have one problem prepared for you guys, but don't worry, it's going to take up some time, quite some time. So what we're going to do in this one is basically verify Stokes' theorem. Stokes' theorem. Just as we did with Green's theorem, right? So what we're going to have to do is, well, here's our theorem first of all, is that the line integral over the boundary of S of f dot t ds is equal to the surface integral, so the double integral over of the curl of f dotted with the normal vector and then ds. So again, just as we did with the Green's theorem problem, if you watch that, what I'm going to do is approach this in a kind of systematic way. So the first part is going to be solving for the left side, okay? And the second part is solving for the right side separately. And then the last part, which is pretty much the easiest and most fun in my opinion, is comparing the two sides and seeing our two results and making sure that they are equal, okay? So in this case, our example is going to, well, I'll write the information on the next slide. So our surface S is the surface of the cylinder. So surface of a cylinder with radius 2. So radius equals 2. And the z, our height goes from 1 up to 6. Okay, and it also tells us the orientation, so it is oriented with outward pointing normal. And our given vector field with which to integrate is yz squared, 0, and 0. Okay, so let me draw a quick picture of this to give you guys a visual of what this looks like. So we're going to have our x, y, and z. We have 1, 2, 3, 4, 5, 6. 1, 2, 1, 2. Okay, so our circle, our cylinder starts about here at height 1, right? And it goes up to 6. So something like that, right? And we'll connect the lines here and make a little can-like thing. Okay, so this is what our surface looks like. And what we're going to have to do here is, first of all, we're going to improve the left side of our equation, right? So part 1 was finding the line integral over the boundary of the surface of f dot t ds. Okay, so in this case, we have to figure out what is the boundary of S. So S is the everything, right? Top, bottom, everything. Okay, so this is going to be, well, we can call this C1 on top. Well, no. Sorry. In my notes, I called that C2. And the bottom one is C1. All right, so I'm going to orient this, both of these pointing this way. I don't know if you guys can see the arrows, but it's going around this way, both of them. So then I'll say that, well, okay, so sorry about that. I'm going to backtrack a little bit and say C1 on the bottom here, it's rotating this way in the direction of the arrow, right? And C2, I'm just going to make it real simple and say that it's actually going in the same direction, just to keep it simple, okay? So they're both rotating in the direction of this big arrow at the bottom. Okay, so what we have to do, as I said, is figure out the boundary of S. So here's S, and then the question gives us the orientation of the normal vector. So let's say you're pointing outward. So this is the normal vector here. So this is like some person walking, okay? So some person walking, and as they're walking along in the direction of the arrow, like this, along the top curve, which is C2, the surface is actually on their right side, on their right-hand side. So we need to change that. So we need, so the boundary of S consists of something C1 plus something C2, and we have to decide whether we need a positive or a negative sign in front. And what I just deduced is that when you're walking along C2 in the direction of the arrows, the surface is on our right side, but we want it on our left-hand side. So what we need to do is reverse the orientation with a minus sign in front. Okay, so now let's look at C1. And let's say, again, you're a person down here, and you're walking along, right? So something like that. Okay, so you're walking along the direction of the arrow, and actually the surface is on our left-hand side, so we are good, and we can remain positive with the C1. Okay, so what this tells us is that the this integral here is going to be equal to the line integral over C1 of f dot t ds, and then minus the line integral over C2 of the same thing. Okay, so this is basically what we're going to have to compute for part 1. All right, so from here, we have to parameterize each of these curves separately. So C1 of t can be given by, so we have a circle of radius 2, so that would be 2 cosine t, 2 sine t, and we have a constant height of 1. Okay, so then C1 prime of t, if we differentiate all of these once, we just get negative 2 sine t, a 2 cosine t, and a 0. Okay, and then the top one, or the top curve, so C2 of t, is going to be the exact same thing, because we basically have the same circle, except for at a different height. So it's going to be 2 cosine t, 2 sine t, and this time the height is at a constant 6. Okay, and then we'll just differentiate like normal here to find C2 prime of t. So it'll be the same, it'll actually end up being the same, because the constant just differs, but that becomes 0 in differentiation. Okay? So we have something like that, and now keep these in mind, make a note of them, and I'll move on to the next slide where we start setting up our integrals. So again, I always kind of forget to mention, sorry about that, but our parameter variable, the bounds on them are, on this problem, is 0 to 2 pi, and I usually kind of forget to put those in beforehand because I assume that everything in this case is a closed curve, therefore it must go all the way around, right? But anyways, so I'll work on that, don't worry. And so for C1, anyways, what we have is from 0 to 2 pi, so this is for C1 curve, and then we have y times z, which is, because we need our f dot t, right? So this means f of C1 of t dot C1 prime of t, okay? So just giving you a background on what I'm doing here. So our f was y times z squared was the first component. So y in this case for C1 was a 2 sine t, and our z was just a 1, so 1 squared. And we have a 0 and a 0, and this comes from the f. And we're dotting it with C1 prime of t, so that's negative 2 sine t, comma 2 cosine t, comma 0, and then a dt at the end. So this is just for C1, all right? I'm just doing the first line integral over C1. So this simplifies to 0 to 2 pi, and then when we dot these out, we actually get a negative 4 sine squared t and dt, because the other components just go to 0 because of these zeros here. All right, so this is the line integral over C1, and now I want to just compute the, or not compute all the way through, but set up the line integral for C2. So then we have our second curve, so that's going to be the following, integral from 0 to 2 pi. We have a similar thing going on here, so our y was still 2 sine t, but our z's differed, right? So now it's 6 squared, and then we have our 0 and a 0 again, and then dot it with C2 prime of t, which it actually happens to be the same thing as C1 prime of t, right? That's what we found on the previous slide. Okay, so something like that, right? And then when you simplify this, when you dot it out, we get 0 to 2 pi, and then this actually turns out to be minus 4 times a 6 squared, which is 36, and then sine squared t dt. So this is a negative 144, 0 to 2 pi, sine squared t dt. Okay, and again, this is the line integral over the second curve. Okay, so keep this in mind, or not even in mind. You should write it down on paper, I would recommend, because we're going to be using it on the next slide. Okay, so we're going to be working with those, and what we found at the beginning was that the boundary of S, the line integral over the boundary of S is going to be equal to the line integral over C1 minus the line integral over C2, C sub 2, right? We did that by figuring out the orientation, which was an outward pointing normal, and then making sure the surface is on our left. Okay, so basically what we're going to have is that the entire line integral here of vector field F is going to be equal to integral over C1, so that was negative 4, 0 to 2 pi of sine squared t dt, and then minus, we're going to subtract that from this part here, minus a minus 144 times integral from 0 to 2 pi of the same thing, so sine squared t dt. So as you can see here, we actually have like terms in a way, because we have the same integral here being multiplied times the constants. These turn into positives, so then we get a 140, a positive 140, times 0 to 2 pi of sine squared t dt. Okay, so what this is it's actually, I'll simplify a little bit here and bring a 2 inside so we can make the substitution a little bit easier. So 70, and I broke up 140 into 70 and 2. Okay, so then we have a 2 sine squared t inside. So now we're going to use double angle formula again. So we get that 1 minus 2 sine squared t is equal to cosine 2t. Alright, so then to get 2 sine squared t, we just have to subtract the cosine over cosine 2t. Okay, so now we can just substitute that in for this spot here. So that would equal 70 times 0 to 2 pi of 1 minus cosine 2t dt. Alright, so actually when you do use substitution and all, we've done this in the previous problem, or in a previous problem in the concepts video, but this integrating over a full period for cosine, that brings it to 0. So what we have left is a 70 times 0 to 2 pi of 1, okay, sorry, that's a 1 dt. So that means 70 times t, as t goes from 0 to 2 pi, which means 70 times 2 pi minus 0, which turns out to be, in the end, 140 pi. Okay, so we are not done. Even though we reached this conclusion, this is our answer for part 1. We proved, or we didn't even prove anything. We just calculated the left side of the equation, right? So this line integral here. So this was the left side, and now we need to move on to part 2. Okay, which is the right side of the equation. So part 2, that was, we're going to calculate the surface integral of the curl of f and dot it with the normal vector n times ds. Okay, so f, the vector field f was y times z squared 0, comma 0, okay? And the curl of f, so we're going to first of all compute the curl. So that is equal to, alright, I'll label them, f1, f2, and f3, okay? So what we have is, we're going to have an f3y minus f2z, comma f1z minus f3x, comma f2x minus f1y. Okay, that's a handful. Alright, so what this means is we're going to take the partial derivative with respect to y of the third component. So that's still going to be 0. And then subtract the z derivative of the second component, which is also 0. And then we're going to differentiate the first component with respect to z. So that actually turns out to be 2yz, right? And then we get the x derivative of the third component is still 0 because that's 0. And then again we have a 0. And then the last one, if we differentiate that with respect to y, we just get a z squared. Okay? So our curl is going to equal 0, 2yz, negative z squared. Alright? So that is our curl. And now we have to find, we have to concern ourselves with the surface itself. Okay? Because we need it. We need a parameterization of the surface to find our normal vector, and we also need it to find the bounds, right? So parameterization of surface. So parameterization of S. That's going to be, for a cylinder, we use cylindrical coordinates, so we can use theta and z, and the parameterization is going to be 2, because that's our radius, so r cosine theta, and r sine theta, so 2 sine theta, and then we just, for the z component, we just have a z. Alright, so to find n, remember our tangent vectors here. So tangent with respect to theta, our tangent vector is going to be first derivative of the first component with respect to theta, so that's a negative 2 sine theta. And then for the second one, we have a 2 cosine theta, and the last component we have a 0. And then for t with respect to z, that's going to be a 0, and a 1. Alright, so now we're going to cross them and see what we get. So we have, maybe I should do this on the next slide. Well, I'll try to squish it in here. So we have our normal vector equaling the cross product of these two that we just found. So that's equal to, and we'll set this up, so I negative 2 sine theta, 2 cosine theta, and 0, 0, 0, 1, and j hat and k hat. Alright, so this is what we have, and we're going to end up with I times, and then we have these two being multiplied, so 1 times 2 cosine theta minus 0, and then minus a j hat, and we have these ones now, so then we get negative 2 sine theta, and then minus the 0, and then k hat is just going to be times 0 minus 0, right, because when you do k hat, then you multiply these two first, which is 0, minus these two, which is also a 0. So our normal vector is going to turn out to be a positive 2 cosine theta, comma, and this turns into a positive 2 sine theta, and then our last component is just a 0. Okay, so we solve for our curl of f, and we solve for n, and we also need one last thing, which is the parameter variable domains. So the domain of the parameter variables, which for this case, we want theta to go all the way around, right? We want to complete the cylinder, so that means that theta goes from 0 to 2 pi, and our z, we're actually given that in the problem, right? So that goes from 1 up to 6, okay? So now we can, well, we'll move on the next slide. So our curl of f, I'll just compute this first before we plug it into the integrand. So curl of f dot n. So let's solve for that. So our curl turned out to be something like 0, 2yz, negative z squared. And if you dot that with our normal vector, I'm just going to put everything into polar coordinates now, or into cylindrical coordinates, I suppose. So if we move into cylindrical, our 2 times y is now a 2 sine theta, okay? And our z is still z in cylindrical. And then we have negative z stays z. And then we're dotting this with the normal vector, which we found to be 2 cosine theta, 2 sine theta, and 0. Okay? So this turns out to be, I'll simplify the first one. So 0, 4 sine theta z, and then we have a negative z squared, and 2 cosine theta, a 2 sine theta, and a 0. Okay, so we're going to dot these out. So the first product that we get is a 0. The second one is going to be an 8 times sine squared theta, z, and the last one is also going to be plus 0. Okay, so our final result for the integrand is going to be 8 times sine squared theta times z. Alright, so now let's plug this into the actual integral. So we have the double integral over s, so the boundaries for s, again, were 0 to 2 pi for theta and 1 to 6 for z. And then we're going to plug in the 8 sine squared theta times z here. And then we have to match up our differentials at the end. So that'll be dz d theta. Okay, so now let's just start integrating. So I'm going to bring this 8 outside in front there, so we don't have to deal with it right now. So we get 8 times the integral from 0 to 2 pi, and then what we get is we're integrating with respect to z, so the sine squared theta, it just stays there, sine squared theta. And then for the z component, here we have 1/2 times z squared, as z goes from 1 up to 6, okay, and our d theta. Alright, so now what we end up with is this 8 and 2, 8 and 1/2, simplifies to 4, so we get a 4 in front and a 0 to 2 pi, and then our sine theta is still there, sine squared theta, and then z squared, so if we have 6 squared minus 1 squared, and then d theta, so this is a 4 times 36 minus 1 is 35, so 4 times 35 turns out to be a 140, and then we're multiplying it times 0 to 2 pi of sine squared theta d theta. Okay, so again, we're going to be using the double angle formulas here. So sine squared theta turns out to be 1 minus, okay, so this is equal to 1 minus cosine 2 theta over 2. Alright, so we're going to replace that here. So if you bring out a 1/2 in front, that would make that a 70, okay? And then this goes from 0 to 2 pi still. And we have a 1 minus, that was sloppy. A 1 minus cosine 2 theta and a d theta. Okay, so again, in the integration, this goes away because we're integrating over a full period. So we get 70 times the integral from 0 to 2 pi of 1 d theta, which we found to be 70 times 2 pi, which is equal to 140 pi. Okay, so this is the answer to part 2. This is our approach from the right side. Okay, so in the last slide, I'll do step 3. So step 3 was saying, so we're going to take the our answer from the first part. So this is step 3 here. And this is our answer from the first part. And this is the equal sign that we're questioning. Are these equal? And the second part, our answer was from calculating this, right? So something like that. So this was part 2. And now this is part 3. So for this part, we got 140 pi as our result. And then for this part, this was 140 pi as well. So by equivalence, I guess, 140 pi equals 140 pi. So we have just verified Stokes' theorem. Okay, so yay. Really happy that they came out equal. That's always enlightening, right? Okay, enlightening, inspiring, one of those things. It's very rewarding when you get the correct answer. So it might take a while to get there, and it might take a lot of trial and error, but you know, once you get there, that's always good. So that was an example of verification of Stokes' theorem. Sorry it was so long, but I felt like it exemplified the process of what we're doing and why we're doing it. So, okay, that wraps it up for this video. So good luck with your homework and with studying for everything that you might have coming up.
Back into the man I used to be.